Okay, hi. So now we're going to continue on the chapter 8, but this time I will explain on the boundary value problem using weight differentiation method. Okay, so basically in weight differentiation method, the condition at the boundary is not being given in a value of fixed number, okay, but it will be given in a derivative formula or derivative equation, something like this at the first boundary and at the second boundary. Okay, so if the question give you the condition at the boundary as an equation, okay, so meaning that automatically you're going to do the differentiation method for you to find the value of the effects of the data set. Okay, so in this question, it's been given that y double prime minus xy equal to x powered by 3 minus 4 over x powered by 3, and the data was given in between x1 and 2. This is the 2 point or the two intervals that you're going to find the value of the fx. Okay, and at the condition at the boundary, you have the condition at the first point or the start point, y prime 1, or at the start when x equal to 1 is 4, and the y prime 2 or the condition at boundary 2 or the at end point is y prime minus y equal to 1.5. Okay, and the step size or the hash value for this equation is 0.2. Okay, the same with what you have done on the without differentiation method, you also have to go through the 5 major steps that I've mentioned in the previous video. Okay, so here in the step 1, you have to first draw the diagram ordinate to show your data set and also all the things, all the information that you have from the questions. Okay, so this is your diagram ordinate. At the x-axis, you have x naught, which is the start point, which the value of x is 1, and also your last point or x5, where the value is 2. So this is to comply with the data range that been given by the question. Okay, and in between you have a few datas. Okay, this data having intervals of 0.2, meaning that the second point is 1.2, okay, and the third one is 1.4, and then 1.6, 1.8, and finally is 2.0. So this shows that your step size or your delta x is equal to 0.2. Okay, so it's the same for all data over here. Okay, and then in this case, the value at the boundary is not given as a fixed number. So it was given in a derivative formula or in a derivative equation of y prime at the start point equal to 4, and at the second boundary, the y prime at the end point minus y equal to 1.5. So from here, you have to find the derivative formula for the extended data set. Okay, over here you have data between 1 and 2, but using derivative formula, you actually need to create another data over here before the x naught. This is y negative 1. Negative 1, because this is 0, this is negative 1. And then the other one is over here, okay, on the derivation. At this point, the value will be y6. This is y5. You extend the data into y6. Okay, this is these two values. Okay, you will use as a boundary condition for you to do the equation later on. Okay, so this is the extended data that you have to do using weight differentiation formula. Okay, so now we have to find the value at the boundary first using derivative formula. So it's been given, okay, in the question, y at the end start point is equal to 4 and y at the end point is equal to y prime minus y equal to 1.5. Okay, now we go to the first boundary first. Okay, so now you have to you have to substitute the y prime over here using the derivative formula given by this chapter. So this is the derivative formula for y prime. So we just substitute into this formula. Okay. So this y prime will become yi plus 1 minus yi minus 1 divided by 2 hash equal to 4. Okay. And then, so at this point, at the start point, meaning that your I is 0, so this will make this equation to become y1 minus y negative 1, okay, equal to 4 times 2 hash is 0.2. Okay, now y1 minus y negative 1 is 1.6. Okay, so because at boundary 1, as I mentioned before, you're going to form the equation to become at as a 1 negative 1 equation. Okay, so y negative 1 equation. So this will make this equation to be simplified to become y negative 1 equal to y1 minus 1.6. So this is your final boundary condition. Okay, so this is at the first boundary. Now we go to the second boundary over here. Okay, so I'm using the boundary condition given by the question, and I also have to substitute the first derivative form equation to this equation. Okay, so the first derivative equation it become yi plus 1 minus yi minus 1, okay, divide by 2 hash, and then this is this one, and then minus y2 is actually at point at the second boundary, or at value x equal to 2, which is at the same as I equal to 5. So I just replace y5, okay, equal to 1.5. Okay, and then simplify this formula or this equation. This I is equal to 5. 5 minus 1, y6. Why we use 5? Because at the x equal to 2, this is equivalent to x5, where the I is 5. Okay, so y6 minus y5 minus 1 is 4, divide by 2 times 0.2 minus y5 equal to 1.5. Okay, so simplify this for this equation, it will become y6 equal to y4 plus 0.4 y5 plus 0.6. So this is your second boundary condition. Okay, so now you have already got the equation for both boundaries. Okay, and then so you have the equation for both boundary over here. Then you can start to do the create the linear equation using all the data that you have in step 1 and also step 2. Okay, now we are at the step 3. Okay, in this step 3, you have to rewrite the equation in a finite different format. So this is the equation, or this is the equation that been given by the questions. Okay, now you have to rewrite it in a finite difference format. So in a finite different format, meaning that you have to change the second derivative, okay, of y, or the function, become to this, okay, formula. Right, this is the formula given by the textbook. Okay, so it will be so we just substitute the y double prime, okay, using the second derivative formula. So it will become yi plus 1 minus 2yi plus yi minus 1. Okay, divide by hash square. So this is your y double prime. Okay, and then minus xi yi equal to xi powered by 3 minus 4 over xi powered by 3. Okay, so this one is the substitute of the second derivative formula into the original equation of your problem. Okay, and from here you have to replace. Okay, you have to replace the hash equal to 0.2, and also you have to simplify the formula. Okay, so you can find these steps in my slide. Okay, and as a conclusion, or I just jump into the final equation. So this equation, after I replace the hash value and also after I simplify the whole equation, okay, the whole equation, the final equation will become yi plus 1 plus yi minus 1 minus yi 2 minus 0.04 xi equal to 0.04 xi powered by 3 minus 0.16 over xi powered by 3. Okay, so this is your final equation that you're going to use to replace to do the derivative or to create the linear equation formula. Okay, after replacing the I value equal to 0, 1, 2 until n. Okay, in this question, meaning that you're going to replace, okay, the I value equal to from 0 until from I0 until I5, the maximum of 5 over here. This is 5 in the question. Okay, because all the y value that we have in the data set, we did not have the value. We only been given the boundary condition in an equation format or in question form. So we have to find each y, okay, in the data set and for the solution using the matrix. Okay, now we're going to continue on the step 4. So this is basically your final equation that you get from step 3. So in the step 4, you have to use this equation and replace the I value using differentiation method. Okay, for this differentiation method, you basically have to replace the I for all data set from 0 until 5. Okay, now we go step by step to form the linear equation using this step 3 equation that you have simplified earlier. Okay, so for I equal to 0, so this is the equation. Okay, so just rewrite by replacing all i's in the equation, in the formula, in the equation to 0. Okay, so y 0 plus 1 is 1 plus y 0 minus 1 minus 1 minus y 0. Okay, 2 minus 0.04 x 0 equal to 0.04 x 0 power by 3 minus 0.16 divided by x 0 power by 3. So this is all the this is the equation, okay, after you replace all I using 0 by 0. So from here, what are the x that you have is x0. So you have x0 over here. And what is the value for x0? Okay, refer back to your diagram ordinate in your step 1. Your x0 is equal to 1. So your x0 is 1.0, and then you have to replace x0 equal to 1.0 in the above equation. Okay, so just replace. Okay, to replace the value of x0 over here, you can create using your calculator. Okay, you just create the formula using your calculator. So for example, okay, before you start to do to set the formula inside the calculator, make sure the mode of the calculator has been set into the radius or rad. Okay, and then you can type. So this formula or this equation will be 2 minus 0.04x. So alpha x, okay, and then put calculate. When x is 1, the value will become 1.96. So you can just replace over here. Okay, so this will make this formula to be, this equation to be 1 plus y negative 1 minus 1.96 y0 equal to this one. You just create, clear the screen, and then create another formula into your calculator for this one. Okay, for the whole things. So it will become 0.04 alpha x powered by 3, okay, minus so this is negative, sorry, this is 0.16 divided by alpha x powered by 3, and then calculate. For x equal to 1, the value is 6 over 25, which is 0.24. Is it correct? Oh, sorry, this one is wrong. 0.04. I missed 1 0 over here. This 0.04. Okay, and then calculate. When x is 1, the value will be negative 0.12. So negative 0.12 over here. Okay, so from here, simplify the equation, rearrange according to the sequence of the y. Okay, for example here, okay, this will be y negative 1 plus minus y0, okay, minus 1.96 y0 plus y1 equal to negative 0.12. Okay, over here you list down all the y's that you have on the note column. Okay, so you have y negative 1, you have y0, and also you have y1. Okay, so y negative 1, okay, from here you have to go back to your boundary, because y negative 1 is your boundary. Okay, it's the derivation at the boundary here. Okay, so from boundary 1 formula, we get the equation for y negative 1 equal to y1 minus 1.6. Okay, so this will be y1 minus the value that you get from the boundary. Okay, can you see it? Okay, here y1 is equal to y negative 1 is equal to y1 minus 1.6. This is value at boundary. What about y0 and y1? Do you know the value? y0 we don't have the value, and also y1 also we don't have the value, so it will be a question mark to you. Okay, so over here you know the value for y negative 1, so what you have to do, you have to substitute y negative 1 equal to y1 minus 1.6 into above, okay, equation, to this equation. Okay, so substitute this y negative 1. Okay, so it will be y1 minus 1.6 minus 1.96 y0 plus y1 equal to negative 0.12, and then simplify again. Okay, so this will give you the final equation to be negative 1.96 y0 plus 2y1 equal to 1.48. So this is your linear equation number 1. Okay, so this is your linear equation number 1. You have to repeat the same step, okay, for I equal to 1 until I equal to 5. Okay, the same procedure. Okay, you have to rewrite back the equation over here. Okay, from step 3, rewrite back the equation by replacing the I value according to your I, okay, your current I, and then you have to check what are the x value that you have created, ataupun that has been produced in your simplified equation. Okay, and then replace the value for x for that particular equation, and then you have to define what are the y that you have in your simplified equation and substitute the value if you have, but if you don't have, meaning that you have to leave it in question mark. Okay, so you're going to repeat these steps. I'm going to show the final answer for y1 until y5, and then we can go to the step 5 after this. Okay, so to cut short the video, I have complete all the procedure, okay, in the table. So for this is the equation that you get, the final equation that you get from step 3. So you have to replace all the I value using the weight differentiation method, whereby the I will be start from 0 until the n value. So how you going to know what are the value of I is actually you go back to your diagram ordinate. Okay, you know that you actually don't have the value for all y for your data set over here. What you only have is the condition at the boundary in a form of equation. Okay, the equation that represent the derivative equation for your boundary condition, you have do it in the step 2. Okay, so in the step 2 you have get the boundary condition equation as y negative 1 equal to y1 minus 1.6. This is equation number 1, and then the boundary equation at boundary 2 is y6 equation over here, equation number 2. Yeah. Okay, so what you have to do, okay, you have to, in each step, you have to replace the I value according to the respective I, okay, to the equation final equation at step 3. So replace all the I value, and then you replace the value of, define what x that you have over here, okay, bring it out to the node. Okay, so for the I0 you have x0, and you know from your diagram ordinate the value of x0, okay, ataupun nilai x kosong is 1. Okay, so x0 is 1. Okay, and then you have to substitute the value of x0 from inside this formula. Okay, so after you substitute, you simplify. Okay, so this is the substitute formula. So from here, okay, you take out all the y that you have. Okay, for example, over here you have y negative 1, y0 and y1. So list out in the node y negative 1, y0 and y1. Okay, if you know the value, okay, y negative 1 is actually, you have derived the equation or the formula in the step 2 during the boundary condition. So y negative 1 is equal to this. This is equation 1 in the step 2. Okay, y0 you don't know. Okay, y1 you don't know. Okay, and then you have to replace the y negative 1 inside this equation and simplify it to become your final linear equation. Okay, number 1. Again, you're going to repeat the same steps or the same procedure in your next I. Okay, this is I1. When I equal to 1, okay, replace all I in the step 3 final equation into 1. Okay, this is what you get. Bring out the x value out. Okay, so over here you know that the x1 is 1.2 from the diagram ordinate, and replace the x1 value and simplify the equation. Take out all the y. Okay, so this is all the y which you don't know. Okay, so this become your final linear equation number 2. And then the same goes to your I2, 3, 4 and 5. You're going to list all the value of x and y that you want to find in each I value. Okay, from here you're going to form a final linear equation, okay, based on the I. Okay, since over here you have 6 steps or 6 procedure to be done. 1, I0, I1, I2, I3, I4 and I5, meaning that you're going to have 6 linear equation, okay, at the end. So then after you have formed the linear equation, you're going to use all the 6 equation and form it as a one system of linear equation and do the solution using metric. Okay, now we have arrived at the final step, which is step 5. So from step 5, what you need to do, in the step 5, what you need to do, you have to write all the linear equation that you have formed in the step 4, from linear equation 1 until linear equation 6. And you have to form them as a system of linear equation. So from step 4 previously, okay, list all the linear equation that you have created, okay, over here. And this is one system of linear equation, and from this one linear system of linear equation, you have to rewrite it again in a metric format. Okay, so this is the metric format for your system of linear equation that you have created. Okay, so from here you have to find the value of y0 until y5. Sorry, this is error. Y0 until y5. Okay, using any suitable metric solution. Okay, you can use any suitable metric solution that you have learned in the previous chapter or in the earlier chapter, and to find the value of y0 until y5. Okay, so you can see the final answer for this example in my slide. Okay, so that's all for the boundary value problem using with differentiation method. Okay, I hope you can go through the slide and also using this video as a guidance and for you to try again by yourself to do the solution. So if you have any problem, you can contact me directly. So thank you very much. I'll see you after.